Hello everyone, I'm Beini Xie from Tsinghua University. It's a great honor to have the opportunity to introduce my work, Adversarially Robust Neural Architecture Search for Graph Neural Networks. First, I will briefly summarize our paper. The main purpose of this paper is to search for robust GNNs under adversary attacks. Around this topic, our paper have the following key contributions. First, we propose a novel, robust search space by designing defensive operation candidates. Second, we design a robustness metric to search for the optimal robust architectures. Finally, we could understand adversarially robust for GNNs from an architectural perspective. Next, I will introduce our paper in detail. Here is the background information of our paper. Graph neural networks are notorious for their vulnerability under adversary attacks, especially in risk-sensitive domains such as finance and healthcare. Here are two motivations of our paper. We find that existing GNN defensive methods neither guarantee performance facing new adversary attacks nor provide insights to understand GNN robustness. Graph neural architecture search has the potential to solve this problem. However, current graph-NAS approaches lack robust designs and are still vulnerable to adversary attacks. Here I list the paper contributions in detail. It is the first time in literature to consider robust designs in graph-NAS. Especially, we propose a novel robust search space and we design a robustness metric. The experimental results show a large improvement of our methods under heavy attacks. First, I will introduce the problem formulation of this work. The target of this work is to find optimal GNN architecture alpha star from the whole architecture search space by maximizing the classification accuracy and the architectural robustness metric. Here we display the overall framework of our work. Given a clean graph, the supernet built upon our robust search space is trained in a single pass one-shot way. Inside the message passing layer, we construct the graph structure mask operations, which could potentially defend against attacks. Then the attack proxy produces several adversary samples based on the clean graph, and we search for robust graph neural networks with the proposed robustness metric. Finally, we evaluate the optimal robust graph neural networks on perturbed graphs. Next, I will introduce our methodology in detail. The design of our search space follows the message passing paradigm of GNNs. In one message passing layer, which is also called the intra-layer design, the graph structure mask operations M will process the current graph structures. The other operations include the correlation coefficients, which calculate the neighborhood information, and the aggregation operators, which aggregate the neighborhood information, and the combine functions, which combine self and neighborhood information. Specifically, we contain 5 candidates in graph structure mask operations. They are identity, low-rank approximation, node feature similarity, neighbor importance estimation, and variable power operator. The adjacency matrix in the else layer is calculated by the Helmholtz product of the original adjacency matrix and the graph structure mask in the else layer. After introducing the search space, here we show our designed robust metric. Intuitively, the performance of a robust GNN should not deteriorate too much when we confronting various perturbed graph data. Here we use KL distance to measure the prediction difference given clean and perturbed data. Here, A prime indicates the adversary samples by our attack proxy. We evaluate the expectancy of the mean distance between embeddings of clean data and adversarial samples. A larger R indicates a smaller distance between the prediction of clean data and adversarial samples, and consequently a more robust graph neural architecture. We evaluate the robustness metric by randomly choose 300 architectures and draw two-port plots. The left plot is the histogram of the robustness metric in log scale. The right side is the bar plot shows the mean accuracy decrease for different R intervals. The accuracy could be regarded as a ground truth measurement of the actual robustness. We could see that the mean accuracy decrease has a negative correlation with respect to robustness metric, and this phenomenon indicates that our robust metric could successfully filter robust architectures. Next, I will introduce main results in our paper. The table in this slide shows the defensive performance under non-targeted attack, and the yellow highlighted area is the result of our proposed method. We could see an obvious improvement by other baselines, especially when the groups are heavily attacked. In this slide, we draw a box plot on Cora dataset, where the first row of each picture is the clean test accuracy for various operations, and the second row is the accuracy decrease under attacks, and the lower is better. We could find some interesting phenomena. For Cora dataset, NFS is the most effective operation for pre-processing perturbed graph data, and GCN is the most fragile correlation coefficient under attack. For neighbor aggregation operations, SUM shows high accuracy and a relatively robust performance. Also, combination functions are essential to enhance the robustness of GNNs, as we could see a smaller accuracy decrease using GIN and SAGE operations. Most interestingly, increasing the model depth makes GNNs more fragile under adversarial attacks. A two-layer GNN shows reasonable good performance for a Cora dataset. Here is the whole content of our paper. Thanks for listening.